What if I told you this VR headset could measure your brain waves as well as an EEG, and that this tattoo can measure your heart rate better than any of the latest Apple Watches? These devices are called bioelectronics and are transforming the medical industry through a field called material science. Material science focuses on manipulating the physical and chemical properties of materials to engineer amazing technology. We visited Dr. Nanshu Lu's lab at UT Austin's Cockrell School of Engineering to learn how they used material science to create e-tattoos that can measure and wirelessly transmit vital signs, as well as e-skins that give robots a sense of touch. We'll be breaking down 3 innovations, including an ECG/SCG tattoo that measures heart rate, another tattoo that measures blood oxygenation and pulse, and finally a virtual reality EEG headset that measures your brain waves. This is the abstract. Imagine you are preparing for a marathon. You want to monitor your heart rate to make sure you are training correctly. So you wear an Apple Watch, which can give you a somewhat accurate measurement of heart rate. But as you increase the intensity, let's say you decide to speed up, the measurements your watch records becomes more and more inaccurate. Why? Well, it's an intrinsic difference between the chunky, rigid materials of your watch and your soft, stretchy skin. The two surfaces just don't match. Traditional medical wearable devices face a similar problem. This is a big issue for patients who need to wear diagnostics or monitoring devices for extended periods of time. Measurements become inaccurate and also extremely uncomfortable. Dr. Lu and her team researches ways to make electronic devices more compatible with our skin and therefore more comfortable to wear. We asked the Lu lab to show us some bioelectronic devices and some cool properties used to create them. First up, Sarnab showed us a dual ECG/SCG patch. ECG stands for electrocardiogram, which measures the electrical activity of the heart, while SCG, or seismocardiogram, measures the chest vibrations associated with heartbeats. By using synchronous data from both ECG and SCG, we can get a much greater insight into heart activity and heart health.
So here we have our dual mode ECG/SCG patch, but generally it's supposed to be placed straight on the chest and can measure your ECG, because it also has like mechanical sensors that kind of measure how hard your heart is beating. Since it's Bluetooth, it's also compatible with your smartphone. That's kind of nice because it can kind of, be an advanced version of an Apple Watch. As you can see, it's like a mixed electronic and material device. Now you would observe that we have the electronics kind of shaped into these serpentine tracks or serpentine ribbons as we call them, and that is because copper inherently is like a non-stretchable metal. So to make it stretchable so it can stretch with the body, we kind of make this into this serpentine shape. As you can see here, I have one here that's actually encapsulated in like a insulating polymers, and you can actually stretch it without like breaking the copper stuff, which you can't do with normal electronics.
Sarnab described an interesting property on manipulating the shape of an intrinsically stiff metal like copper to make it more stretchable. A great analogy is a metal spring. Metal itself is not a stretchable material, but when you shape it into a helical structure, its properties change so that it can stretch and withhold force. Similarly, the shape of copper drastically affects its stretchability. When you stretch a linear piece, the opposite forces you apply are concentrated along one dimension, causing a thin strip to be easily broken. On the other hand, a serpentine-shaped segment allows for the forces to be distributed in different directions, which allows you to stretch the copper without it breaking, making this serpentine shape an ideal structure to use in various bioelectronic devices. Next, Philip showed us an e-tattoo that measures blood oxygenation through optics. Blood oxygenation is the amount of oxygen in your blood, which is an important indication of a number of conditions, including certain lung and heart abnormalities. There are 2 types of blood oxygenation: arterial blood oxygenation, which measures the oxygen levels in the arteries, and venous blood oxygenation, which measures the oxygen levels in the veins.
Arteries are the vessels that carry blood away from your heart, and then after the cells consume oxygen, the veins bring it back to the heart. You can think of arterial blood as supplying oxygen to the cells. After the cells take the oxygen, there's going to be some oxygen left that returns to the heart. The difference between arterial and venous tells you how much oxygen is being consumed, the extraction rate, essentially.
This extraction rate is called VO2, or volume of oxygen consumed. Resting VO2 measures how much oxygen your body uses when there is no stress. For example, right now as you are sitting down casually watching this video. An abnormal VO2 can tell us many things. For example, when your body fights infections, your cells need more energy, so your body temperature, metabolic rate, and oxygen consumption may increase, resulting in a high VO2. On the other hand, infections that cause your body to have an extreme immune response to the point where your organs start shutting down is a result of your cells not being able to efficiently extract oxygen from the blood. This condition is called sepsis and is a result of low VO2.
So actually, venous blood oxygenation isn't available to be measured non-invasively. That's what we're really working on now. With a pressure sensor, when the pulse expands the artery, you can literally feel when the vessel expands, right? So like you press on your radial or your carotid, you can measure the pulse. With optical techniques, it's a bit different. Actually, when the pulse passes by the vessel, the tissue absorbs more light. There's more blood in that volume of tissue. When you shine light into it, less light will be reflected because it's being more absorbed. If you track that absorption against time, you can actually see the pulse waveform. Here, this is a tiny LED, and then these are photodiodes. By shining light with the LED and measuring the back reflected light with the photodiodes, we can measure the absorption of the tissue.
This is actually very similar to how your watch can track your heart rate and arterial blood oxygenation. In a very simplified explanation, blood appears to be red because it reflects red light and absorbs green light. If you remember the color wheel, red and green are complementary colors, meaning they're opposite from each other on the color wheel. When your heart beats, blood flow increases in your wrist, which causes more green light to be absorbed and less to be reflected. And in between pulses, there's less blood flow, meaning less green light is absorbed and more is reflected. Sensors called photodiodes detect the amount of light reflected during these periods and translate that information into your pulse rate. Finally, Dr. Li showed us a modified virtual reality EEG headset. EEG, or electroencephalogram, is a device used to measure brain activity and diagnose brain conditions such as epilepsy, brain tumors, and sleep conditions. You've probably seen traditional EEG headsets in hospital dramas, or maybe even wore one. Next, Dr. Li explained the obstacles of using traditional EEGs and what the VR headset offers for patients.
VR can provide this immersive environment when you are doing a task or performing a task. So when you are doing it in immersive environment, you will find you have a stronger response in your brain activity. With this EEG, so traditional one are using this kind of EEG cap. So you are familiar with this, right? Apply the electrode, how I apply the electrode. So you need to separate the hair and make skin preparation and to remove the oil on the skin. And then you can inject the gel electrode here. And then you can make the connection with the external recording system. So this is a traditional method. What is the problem living? So one is you need to apply the electrode one by one, separate and inject the gel and to check the contact impedance whether the signal quality is good. If not good, redo it. So the whole setup you'll need almost 1 hour. Another problem is because it is a wet gel and it tends to dry. Our human skin has relatively higher temperatures than our environment, right? So it tends to dehydrate with time. So it becomes dry. The contact between our skin and the electrode is not that good. So that is why with time it will first degrade and then lose its performance. The third problem is, so you apply the gel electrode and then when you remove it, you need to take the shower and if it is not that easy to remove directly, right? So not everyone they have this residue.
The VR headset solves these 3 issues by using soft, spongy electrodes that touch the scalp skin to read and transfer brain signals. These spongy electrodes are coated in a compound called PEDOT, which stands for poly-3,4-ethylene dioxythiophene. By the way, I had to practice like 50 times to say that correctly. PEDOT is a material used in many bioelectronic devices because of its conductive properties, meaning it can transmit signals from the human body to a tracking device. It's also stable, meaning it won't destruct your skin, and it's transparent, so it won't be noticeable by others when it's monitoring your vital signs. However, PEDOT itself is hydrophobic, meaning water-fearing, or it doesn't like to touch water. Hydrophobic materials are difficult to process and modify into usable forms, such as conductive films or coatings. So, researchers add another compound called PSS, polystyrene sulfonate, another long name. PSS is hydrophilic, or water-loving, and when bonded to PEDOT, allows the combined PEDOT-PSS compound to be shaped and manufactured into a usable coating for the spongy electrodes to transmit signals from your brain to a computer. But before PEDOT-PSS can be used in bioelectronic devices, two important qualities must be considered. First, the conductivity, which is how well the material transmits signals, and second, the stretchability, which is how the material flows with your skin's movement. Adding PSS to PEDOT, although important for manufacturing, actually lowers the material's conductivity. This is because when you combine hydrophobic and hydrophilic compounds together, they won't mix evenly. In fact, they spontaneously separate into micelle-like structures, where the hydrophilic, non-conductive PSS forms an outer spherical boundary that contains an inner core of the hydrophobic conductive PEDOT. The issue is that the non-conductive PSS chains block and prevent electrons from traveling through the conductive PEDOT. To tackle this, we add something called a dopant, which is a small amount of a special material that would change the properties of the original compound. In this case, we add a compound called DMSO, or dimethyl sulfoxide. DMSO acts in breaking the hydrogen bonds in between neighboring micelles to allow a pathway for electrons to flow more freely, making PEDOT-PSS 800 times more conductive than the original material. To test out the conductivity, we used a multimeter, which measures the resistance of a material. Resistance and conductivity have an inverse relationship, meaning the higher the resistance, the lower the conductivity, and the lower the resistance, the higher the conductivity. Testing it out, the resistance of the original PEDOT was around 10 kiloohms, and the resistance of the PEDOT with DMSO was around 3.5 ohms. This means that the PEDOT with DMSO can transmit signals significantly faster than PEDOT alone. Next, we tackle the issue of stretchability. PEDOT-PSS doesn't naturally follow the flow of your skin as it folds or expands. For PEDOT to mimic human skin stretchability, researchers add another dopant called a plasticizer, which is something that will make a material more flexible and bendable, like plastic. So how does it work? PEDOT and PSS are linked mainly by ionic bonds, which are strong and hard to break. Individually, intermolecular forces are easy to break, but because there are so many of them, all these weak attractions actually add up to a pretty strong force. A plasticizer such as glycerol works by inserting itself between PEDOT and PSS chains to reduce the intermolecular forces, causing there to be some spacing between the two chains. This spacing allows PEDOT and PSS to move freely, resulting in the material's flexibility. To demonstrate this, Dr. Li transferred PEDOT-PSS with and without added plasticizer onto my skin.
Okay, it's time to see the difference.
Ooh, wow, it broke so easily. Okay.
You see, if I stretch too much, see.
Oh, wow. As you can see, the PEDOT-PSS without plasticizer broke way more easily than one with plasticizer. For fun, Dr. Li showed us an even stronger and more flexible material that I later tested out with my friend, and it wouldn't break no matter how hard we stretched it, until the tape itself broke. This ultra-stretchable material was created by binding PEDOT-PSS to a polymer matrix, which we've conveniently linked some resources for you to explore in the description on your own. And with that, we have now transformed the properties of PEDOT, which is one of the most important materials in bioelectronics, to make it exponentially more conductive and stretchable to use on human skin.
So you can apply it to the place you want to collect the signal. For example, if I can place it on the wrist, so I can collect our ECG signal about our heart. And if we place it on our forehead, so it can collect the signal from our brain.
We hope this introduction gives you a taste of just how cool materials science is and how it's applied in breakthrough research. You can learn much more about the Lu Lab's work at UT Austin from the links below. Their research is changing the face of medicine, and we encourage you to read more about it. Thank you for being curious with us on The Abstracts.